Greetings. In our first part of the video, we managed to derive some very basic equations for calculating the gas turbine cycle. And in this part, we would try to put numbers into those equations and then draw some further understanding of the cycle. Now, I would use these equations to do some calculation. Now, as for the compressor, we start from this equation for the process, and we know that T2 over T1 equals P2 over P1 to the power gamma minus 1 over gamma. And putting numbers to it, T2 would equal 273.15 times 8, which is our pressure ratio, to the power 0.286, which is gamma minus 1 over gamma, and I've assumed gamma to be 1.4. So T2 would equal 495 kelvins. This is the value for the compressor exit. Now, how much work does the compressor do? W for the compressor is Cp0 times T1 minus T2, which equals 1.0045 times 273.15 minus 495, and the outcome for the compression work would be minus 223 kilojoules per kilograms. This is the work required to compress every kilogram of work from 100 kilopascals to 800 kilopascals. Now, this is for the compressor. Now we go for the combustion chamber and see what do we have for the combustion chamber. And this equation comes to our help. Q for the combustion chamber equals Cp0 times T3 minus T2, which would equal 1.0045 times 1500 minus 495, and Q for the combustion chamber would equal 10 kilojoules per kilograms. This is the heat that must be added in the combustion chamber. Now, the problem tells us that this turbine runs this compressor. So there should be equal work between these two. The work of the turbine is calculated from this equation. The work of the compressor is calculated from this equation. And if they are two equal, then we should be able to write 0 equals Cp0 times T1 minus T2, which is the work required for the compressor, plus Cp0 times T3 minus T4, which is the work produced by the compressor turbine. And we know a lot of the values. We know almost everything. Cp0 cancels out, and T4 would equal T3 minus T2 plus T1, and that would be 1500 minus 495 plus 273.15, and T4 would equal 1278.15. And this is the temperature at point 4. You see, this is T3 and this is T4. The process between 3 and 4 is isentropic. We know the pressure at T3. We know both temperatures, so we would be able to calculate P4 because this is an isentropic process. What should we do is this. We should write P4 over P3 equals T4 over T3 to the power gamma over gamma minus 1. I'm putting numbers to it. This equals 800, P4 equals 800, which is P3, times 1278.15 divided by 1500 and to the power 3.5. And the outcome for P4 would be 456.9 kilopascal. So this much pressure from 800 to 456.9 is lost just to run this compressor. But we still have the rest to do useful work. We could get useful work from the rest of it. So if we want to calculate 0.5, we could write it like this. T5 for the rest of the turbine work, we could write T5 over T4 equals P5 over P4 to the power gamma minus 1 over gamma. And that gives us T5 to be T4, which is 1278.15 times 100 and divided by 456.9 to the power 0.286. And this gives us T5 to be 827.7. This is 827.7 kelvins. You see, this is quite hot. Yeah. And this is why I said it is used in steam turbines to heat their boilers instead of burning fresh fuel. to heat the boiler of a steam turbine, this hot air could be channeled into the boiler of a steam turbine, and that's what's called the combined cycle. We shall come to that later on, but it is notable that this could be used to heat this air from point 2. Point 2, what was that? What was the temperature there? The temperature of point 2 was 495. You see, to heat a 495, it is to heat a 500 Kelvin air, we have here 827 Kelvin. So we could have used this air to heat the outgoing air from the compressor, which is not done very often. Or alternatively, we could use this air to heat the boiler of a steam turbine, which is quite common. So still, the important point is to note that there is air here which still have some availability and still can produce work. So we did our calculations for what is called the gas generator. The gas generator is the compressor and the turbine that runs that compressor. As it is called, the gas generator generates hot gas at high pressures, and that gas may be used in a turbine to get more work. So now that you have calculated what is available to that, what is available after that gas generator, we will also calculate the work that's possible to get from it. So W for LP turbine, which is the low pressure turbine, or as it is called sometimes, the power turbine, equals CP0 times T4 minus T5. And that equals 1.005 times 1278.15 and minus 827.7. And the work for the power turbine would be 452.7 kilojoules per kilograms. You see, it's interesting that we the compressor required 223 kilojoules per kilogram of work, which the high pressure turbine actually provided that work. So what is left for us? There is still 452.7 kilojoules per kilogram of work, which is now left and may be used to produce, say, electricity in a generator. If the power of the power plant is, say, 200 megawatts, if power P equals 200 megawatts, then the mass flow required is P over W, which is 200 times 10 to the power 3 divided by 452.7, and that gives us 441.8 kilograms per second, which is a very, very large mass flow rate, and that's not unusual for large power plant gas turbines. But, we have calculated the mass flow rate, the power, and everything. Now, the next step is to calculate um, efficiency. And to calculate the efficiency, what we need to do is to see what we have gained. This is the power and what we have spent for it. And that is the heat that we have spent for it. So the efficiency is eta equals what we have gained, which is the work by the power turbine, 452.7 kilojoules per kilogram, and the heat that they used to heat the gas turbine and they used for process 2 to 3, which is 10 kilojoules per kilogram, and the outcome would be 0.448, which means it is 44.8% efficiency. Just to have a knowledge of what this efficiency means, whether it is a low efficiency or high efficiency, we could always start with the Carnot efficiency. Eta of a Carnot equals 1 minus TL over TH, and that equals 1 minus 273.15 divided by 1500, and that equals 81.8%. So it might seem that this is not a good cycle since uh, it has a far lower efficiency than the Carnot cycle. But please note, the Carnot efficiency was calculated for a constant temperature heat addition. We have not added all heat in this temperature. Some of the heat addition has started from around 500 kelvins and it has gone to 1500 kelvins. So a more reliable, a more realistic value would be somewhere around 1000 kelvins. And in fact, if we allow here to be 1000, then the ratio would be different and we would get a lower Carnot efficiency. Now, still, for a gas turbine, this is a good efficiency anyway. Your real gas turbines, as you shall see, have lower efficiencies. Another reason, since we have got lower efficiency, is because we have selected a lower pressure ratio. In gas turbines, efficiency increases with pressure ratio, as I mentioned earlier. We have selected a lower pressure ratio. 8 is a lower pressure ratio, and if you have selected a pressure ratio of, say, 15 or 20, which is not unusual for this temperature, then we would have gained more work, and for more work, we would have gained a better efficiency. In fact, the work would be larger and the heat required in the cycle would be smaller. So it was possible to get a better efficiency if we had selected our numbers more carefully, and but that is how the problem goes. Now, um, the next step that they sometimes do is to do reheat. What does a reheat do? A reheat just Heat, instead of expanding the air in the process 4 or 5, we may again heat the process to a point, say 6, and then expand it to a point 7. What do we get? Of course, two things result from such action. First is that between 6 and 7, the possible work from expansion is larger than the work that it could possibly gain between 4 and 5. So overall, we may gain more work. Would it be more efficient? It's unlikely, and it won't. Why? Because we have added a smaller cycle to our larger cycle. So this smaller cycle would have a smaller efficiency because it has closer, higher, and lower temperatures. You would have done a lot of heat, you would have given a lot of heat, and we wouldn't have gained that much extra work for the heat we have done. Point 7 would be warmer. Why? What's the good of it? Point 7 would be warmer, so if we send this into a boiler, in fact, it could heat that boiler much better than what point 5 could do. It is not that popular in gas turbines to say reheat. What they call it is reheat. This is not very popular in gas turbines, but what I shall do now is to calculate it and show you all I have just said in numbers. Okay, let's place it here, and Q for the reheat, Q for the reheat equals Cp0 times T6 minus T4. T6 minus T4. This is the added heat for the reheat. Calculating it is equals 1.005 times 1500 minus 1278.15, and Q for the reheat is 223 kilojoules per kilograms. Why? Is that a familiar number? Yes, it is. In fact, this value is the work that we had calculated for this compressor. You see, it's the energy equation. We use this work to compress air. Now, this turbine had done the same work to compress air. Where did this work come from? From that turbine. And this turbine did the same work to compress this air. So it lost 223 kilojoules per kilogram of energy. And now we have to replace that energy. How much energy do we need? 223 to go back to point 6 with a similar energy as point 3, but with a different pressure. Okay, now T7 equals T6 times P7 over P6 to the power gamma minus 1 over gamma, which equals 1500 times 100 divided by 456.9 to the power 0.287. 6 and T7 equals 971.4 kelvins. You see, T5 was 827 and T7 is 971, which, as expected, 7 is far warmer than 5. Now, we have done all this. How much extra work have we gained in 6, 7? You see, the work we had in 4, 5 was 452.7. Now, how much work have we gained from this process? And the work we have gained is, call it W for reheat turbine, which is CP0 times 1500 minus 971.4, and the outcome would be 531 kilojoules per kilograms. Well, compare it with 452 kilojoules per kilogram we had. So what we have done, we have spent 223 extra heat to warm the air, and for this we have not gained as much extra work. So we can't expect higher efficiency. The efficiency for a reheat cycle, reheat equals 531 divided by, which is the useful work from that cycle anyway, divided by 1010, which was the heat in the initial first combustion chamber, plus 223, which is the heat from the second combustion chamber, and the outcome is 0.431%, which is 43.1%. Compare it with the 44%, 44.8% that we had gained from our original cycle. It just means that reheat wasn't that efficient anyway, although we gained some further work. In jet engines, they do reheat the air going out to expand it in a nozzle to supersonic values. They get far more extra energy, much faster work, but it's not efficient. And so usually it is used by supersonic aircraft to pass over this sonic area. I mean, to uh, go from, say, Mach numbers zero point 0.8 to Mach numbers 1.2, so that they would pass over that area faster, or is used by uh, fighter airplanes just to get faster takeoff or faster maneuverability. But for commercial aircraft, they usually don't do that, and also for the for power generating power plants, they also, this is not very common, and they rarely do that. And in the next video, I will talk about the benefits we could get from hot exhaust gases. Cheers.